And today we will cover three small topics. The first one is more about the techniques. The second and third are facts. Okay, let's see the first one, telescoping method. What is telescoping method? Let's see the following example. I need to come up with an example, by the way. Suppose, for example, I want to find the sum from n equals to 1 to infinity of 2 over n squared plus 2n. Now let's find the sum. If it is convergent, and if that's convergent, it's divergent, we need to show that it actually adds to infinity. Okay, so we will start with note that 2 over n squared plus 2n is equal to 2 over n times n plus 2. Now then, we want to do partial fraction decomposition into a over n plus b over n plus 2. Okay, so you do partial fraction decomposition. Fast forward, you will see that 2 over n squared plus 2n is equals to 1 over n minus 1 over n plus 2. Okay, I just do it fast forward. So, the infinite sum from n equals to 1 to infinity of 2 over n squared plus 2n is equal to the sum from 1 to infinity of 1 over n minus 1 over n plus 2. Is it okay so far? Now let s maybe as I equals to the ith partial sum from 1 to I of 1 over n minus 1 over n plus 2. You will see that this is actually equals to the ith partial sum here is equal to, when n equals to 1 plus when n equals to 2 plus n equals to 3, n equals to 4, up to I. So when the n equals to I, it will be 1 over I minus 1 over I plus 2. Now notice that we have some cancellation here. This guy cancels this. This guy later on will cancel here. And this guy will later on cancels something else. Okay, let's do more. Let me do more so that we can see some pattern. Let me do more. So this will be plus 1/4 minus 1/6, 1/5 minus 1/7, all the way to I over I minus 1 minus, I'm sorry, 1. This is I plus 1 plus 1 over I minus 1 over I plus 2. Notice that if I go up to the fifth term, if I go up to the fifth term, this cancel, okay? So I always have nothing cancels this, okay? And up to the I equals to 5, from up to I equals to 5, I get I plus 1, I plus 2. So if I go up to I, it will be 1 over 1 plus 1 over 2, these two things here, minus 1 over I plus 1 plus 1 over I plus 2. Okay, so this is equal to the ith partial sum will be 3 over 2 minus 1 over I plus 1 plus 1 over I plus 2. What we meant by telescoping is like the middle terms, some terms in the middle cancel each other. That's what it means to be telescoping. Like this guy cancel with something in the middle. This guy cancel with something in the middle. This guy cancel with something in the middle. So once you kind of like add them all, some terms in the middle cancel and you end up with this expression. Okay, now then the summation to infinity of that 2 over n squared plus 2n is equal to limit n, I'm sorry, I goes to infinity of the summation from 1 to I of 2 over n squared plus 2n. But we have seen earlier that this guy, this summation here, this is 1 over n minus 1 over n plus 2. And that is limit I goes to infinity of 3 over 2 minus 1 over I plus 1 minus 1 over I plus 2. Right? This is basically limit I goes to infinity of the ith partial sum. Okay, then we see that this is equal to 3 over 2 minus 0 minus 0. That's okay. So the idea of telescoping is basically you rewrite it as a partial sum first and see the pattern of canceling. Then from there, you find the simplified version of the ith partial sum. And then you bring that to the limit. That's the plan. Okay, now some problem actually appears a lot easier than that. For example, number 44. from that 11.2, the sum of n from 1 to infinity of natural log of n over n plus 1. I let Si to be the ith partial sum from n equals to 1 to I of natural log n over n plus 1. Okay, that's the ith partial sum. And we now can write this I partial sum as natural log of 1 over 2 plus natural log of 2 over 3 plus natural log of 3 over 4 all the way to natural log of I over I plus 1. Okay, and then this is equals to natural log of 1/2 times 2/3 times 3/4 all the way to I over I plus 1. Remember, sum of logs equals to log of product. Okay, so you see if I have only 2 terms, this cancels, 3 terms, this cancels, 4 terms, and so on and so forth. I terms, I will have natural log of 1 over I plus 1. Right? Which is equals to actually negative natural log of I plus 1. Remember, 1 over I plus 1 is I plus 1 to the power of negative 1, right? Okay, now then, the infinite sum of natural log of n over n plus 1 is equals to limit I goes to infinity of the nth partial sum. This is equals to limit I goes to infinity of Sn, Si. This is equals to limit I goes to infinity of Si. What is my Si? It's negative natural log of I plus 1. This is negative limit I goes to infinity of natural log of I plus 1. This is negative infinity. Now, with that said, let's do the hard one. I think number 48 is actually quite difficult. Number 48, we need to find the summation from n equals to 2, not from 1 up to infinity of 1 over n cubed minus n. I need you to do partial fraction decomposition for this first. This is 1 over I factor the n. I get n squared minus 1. That's n plus 1, n minus 1. So n minus 1 and n plus 1. Let's call this A, B, C. Now, let me ask you to find that first. And do as far as you can. Okay, maybe in 5 minutes. So 741. Okay, let me try. Multiply by the LCD. I get 1 equals to A times n plus 1 plus b times n minus 1 times n plus 1 plus c times n minus 1. So when n equals to 1, 1 equals to 2a. So a equals to 1 half. When n equals to 0, I get negative b. So b is negative 1. When n equals to negative 1, negative 1, I get 2c. Oh, so c is equals to 1 half. So that 1 over n cubed minus n is equals to 1 half over n minus 1 minus 1 over n plus 1 half n plus 1. Therefore, let Si be the partial sum up to I of 1 over n cubed minus n. That I partial sum, actually it's not really I partial sum, I can say that's the sum to ith term only. That's equals to 1 half over n minus 1 minus 1 over n plus 1 half n plus 1. So when n equals to 2, I get 1 half over 1 minus 1 half plus 1 half over 3. That's when n equals 2. When n equals 3, that's 1 half over 2 minus 1 over 3 plus 1 half over 4. I think I need to do more. 1 half over 3 minus 1 4 plus 1 half over 5. Maybe I do more. I don't see pattern yet, but I guess I need to get more terms. This is plus 1 half over 5 minus 1 6 plus 1 half over 7. Okay, the first 5 terms. Let's see for the first 5 terms how they cancel. The 1/3 here cancel this guy and that guy. The 1/4 cancel this guy and that guy. The 1/5 cancel this guy and this guy. Actually, the 1/2 also cancel at the beginning. Huh? This guy cancel this guy and that guy. See, right? So up to the 5th term, up to the 5th terms, I think I need to go to the I term. So that will be 1/2 I minus 2 minus 1 over I minus 1 plus 1 over I, or 1/2 over I plus 1/2 over I minus 1 minus 1 over I plus 1/2 over I plus 1. Okay, up to the 5th, n equals to 2, 3, 4, 5, 6. So when n equals to 6, this is what I get. When n equals to 6. when n equals to 6, I get 1/2 over 6 minus 1/6 plus 1/2 over 7. Is that a negative number? Why I get negative number? Am I canceling too many things? Hold on. No. I make a mistake here. This guy, and this guy. Actually, only this cancels. So I have extra these. So I have 1/2 over 2 plus that thing. So maybe simplify a little bit. I get 1/4 plus, actually minus 1 over 2 times 6 plus 1 over 2 times 7. The 1/4 here is always there, right? Okay, it's always there. And this is part of the counter. So the summation from n equals to 2 to infinity of 1 over n cubed minus n is equals to limit I goes to infinity of the summation n equals to 2 to I of 1 over n cubed minus n, that is equals to limit I goes to infinity of summation n equals to 2 to I of 1/2 over n minus 1 minus 1 over n plus 1/2 over n plus 1. That is my sum up to I, and according to our computation above, we see that this gives us 1/4 minus 1 over 2I minus 1 over 2I plus 1. And as I goes to infinity, we will get this is 1/4 minus 0 minus 0. So the total sum is 1/4. Okay, so the sum is convergent to 1/4. Now, the thing is, what makes these techniques difficult is you need to actually write enough number of terms to be able to read the sum. Okay, so if you go further, for example, then you will see the 1 get cancelled. If I go further, maybe I use this. This will get cancelled with this, right? Cancel, okay? And you will have everything cancelled except those. You see that? So Si is basically 1/4 plus 1/2 over I minus 1 over I plus 1/2 over I plus 1. Right? Which then this is 1/4 minus 1/2 over I plus 1/2 over I plus 1. That's how we get 1/4 minus 1 over 2I plus 1 over 2I plus 1. That's how we get that. This guy here now gets here. Then we bring the I going to infinity. Okay. Now we usually do this if when we expand the terms, something cancels. Something cancels. Now we do this telescoping if when we do the expansion, something cancels and the partial sum becomes something simple like this, which even though I have to say it's not as simple as we like, but simple enough. Okay, that's about telescoping. Next, the fact. Harmonic series. This series is so well known that they give a name for that. Harmonic series is the infinite sum of 1 over n. Harmonic series is divergent. The proof can be seen in, you can see that in example 8 in our textbook. But basically, this is what it is. S1 let Si be the summation, the ith partial sum of that 1 over n. So S1 is 1, S2 is 1 plus 1/2, S3 is 1 plus 1/2 plus 1/3, S4 is 1 plus 1/2 plus 1/3 plus 1/4, so on and so forth. Okay, now here's the thing. We will see some pattern that S1 is equal to 1. Now notice that for S4, this is greater than 1 plus 1/2 plus 1/4 plus 1/4. Is it okay? I basically replace that one. I say that 1/3 is greater than 1/4. That's what I say. Now, the thing is, on the right-hand side here, you see that this is actually 2/4, which is 1/2, plus another 1/2. That gives you 1. Okay, so you see that S4 is actually, S4 is already greater than 2. You see that? Now, let's take a look on what happened with S8. If I go all the way to S8, there will be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Now, we have seen that this gives us greater than 1, right? And this is actually greater than 1 plus that 1, is this one that we have here, plus 1/8 plus 1/8 plus 1/8 plus 1/8. Which this gives us another 1/2. Which means S8 is greater than 1 plus 1 plus 1/2, which is 5/2. Now, if you go further with this pattern, you will see that as long as the term is 2 to some power, as long as the term is 2 to some power, the 2 to the nth partial sum will be greater than 1 plus n of 2. Maybe I write it this way. This is S4 is 1 greater than 1 plus 2 over 2. S8 is greater than 1 plus 3 over 2. Okay, now doing that pattern, we see that as the 2 to the second partial sum is greater than 1 plus n plus 2. Now the thing is then, when we do limit n goes to infinity of s2 to the n, the 2 to the nth partial sum will be greater than the limit n goes to infinity of 1 plus n over 2, right? Now, but the one on the left-hand side is actually the infinite sum of 1 over n. Is that right? So you see that infinite sum of 1 over n is greater than infinity. So harmonic series is divergent. Now, because harmonic series is divergent, the consequences are consequently first, any scalar multiple of harmonic series is divergent. Second, even if you don't start from 1, let's say you start from n equals to I, as long as it goes to infinity, you don't have to start from the first 1 over 1 or 1 over 2. You can start from 1 over 7, for example. Okay, this is still is divergent. In other words, the divergence or convergence of a series is not determined by the first couple terms. It's actually determined by the infinite terms. Okay, so one thing we know for sure is this. we come up to a divergence test. Divergence test says that if limit n goes to infinity of a sequence does not exist or not equals to 0, then actually I don't like that. I don't like that. I don't like that. That's actually, I don't need this thing. As long as it is not equals to 0, then it is divergent. Limit n goes to infinity of the terms. If it is not equals to 0, then the infinite sum is divergent. Uh, imagine this way, imagine this way. The reason, note the reason that the reason, one of the reasons that the infinite sum is convergent I think I should say one of the reason instead of the reason. One of the reason. One of the reasons that the infinite sum is convergent is that the limit of the terms is 0. Imagine if you keep on adding terms that is not close enough to 0. Imagine if this guy here, as it goes to infinity, as n goes to infinity, imagine if this is not 0. Then you keep on adding something non-zero, right? When you keep on adding something non-zero, then the sum will not stop. You keep on adding something non-zero. Okay. Now, but I have to say this, but simply because limit n goes to infinity of the terms is 0 does not imply the series is convergent. No, it's not true. Okay, why? See harmonic series. Harmonic series is a series where the limit of the term is 0. You see, the harmonic series is divergent even though the term is convergent to 0. Okay, so simply because the limit of the term goes to 0 doesn't mean it will be convergent, no. But we know that if the series is convergent, then it must result in the limit of the term has to be 0. Okay, you can see the proof actually in our textbook, but think about that from intuitively. You see, maybe I give you some intuition. S sub n is the sum, the nth partial sum, and S sub n minus 1 is n minus first partial sum. Okay, now both of them will converge to, suppose the limit exists, it will converge to S as n goes to infinity. That's if n partial sum converges to S. Right? Now, but at the same time, you see that S sub n minus S sub n minus 1 is equals to the nth term. Now, applying limit, n goes to infinity of Sn minus Sn minus 1, that's the same to limit n goes to infinity of A sub n. But on the left-hand side, I distribute the limit. Limit of the n partial sum is S. The limit of n minus first partial sum also S. So the only way that can happen is if, then consequently, the nth term has to be 0 when n goes to infinity. Okay, so notice that the series is convergent. The series is convergent implies the infinite term has to be 0. Okay, from the way I did the proof, the infinite series is convergent implies the infinite term is equals to 0. However, we cannot come from infinite term equals to 0 give us infinite sum is convergent. We cannot. The converse is not true. And the reason is harmonic series. Okay? So divergence test actually says the following. Divergence test says the following. Therefore, if the limit of the term is not 0, then the series has to be divergent. What happens if the limit of the term is 0? Nothing can be said. I write it as a side note. Nothing can be said concluded. Nothing can be concluded about the series either is convergent or divergent when the limit of the term is 0. Okay, that's a warning. If it is not 0, then the series is divergent. If it is 0, nothing can be said. Okay, that's about divergence tests and harmonic series. Let's do problems. For example, number 30. The series from k equals to 1 to infinity of k times k plus 2 over k plus 3 squared. Is it convergent or divergent? Proof. Let the term a sub k be k plus 2 over k plus 3 squared. What is the limit when k goes to infinity? Notice that the degree on the top and the bottom are both 2. Right? So limit k goes to infinity of the k term will be limit k goes to infinity of k squared plus 2k over k squared plus 6k plus 9. Now you cannot do L'Hopital rule, but you don't need to do L'Hopital rule. What you can do, you divide by k squared on the top and the bottom. 1 plus 2 over k over 1 plus 6 over k plus 9 over k squared. This will give us 1 over 1. Because this is not 0, so see, the nth term converges to 1, which is not 0. So the infinite sum must be divergent. Actually, we need to give the reason. If possible, write the reason at the front. So by divergence test, the infinite series is divergent. Number 30, let's do number 30. Number 32, yeah, okay, I'll do number 32. That's way too easy though. The series from 1 to infinity of 1 plus 3 to the n over 2 to the n. I want to say that this is greater equals to the series of 3 to the n to 2 to the n. Right? But that is equal to the series 3 over 2 to the n. Notice that the last one is geometric. With r equals to 3/2, which is greater than 1. Right? So this series 3/2 over 3/2 to the n is divergence by geometric series. And the greater series is divergent and y. We learned that before. Anybody remember? By comparison test. Something we learned before. Okay, even though we will learn that more explicitly later. Of course, number 32 can also be done this way. that number 32 can also be done by separating them. This is the summation of 1 over 2 to the n plus 3 to the n over 2 to the n. Right? And that is equal to the summation of 1/2 to the n plus the series, I should say, of 3/2 to the n. Now, the thing is, but this series, the second part, so you need to argue partially here. This guy here is geometry. With r equals to 3/2, which is greater than 1. So that series is divergent. Now, the thing is, if this part is divergent, then the whole part in which you add something positive will be even more divergent. Okay. Number 36. The series n equals to 1 to infinity of 1 over 1 plus 2 over 3n. So because we have divergence tests, when every time you have a series, the first thing you would like to do is what happens when n goes to infinity? Does the term goes to 0 when n goes to infinity? If not, then you get the answer already. Okay, like in this case, solution. Let the n term be 1 over 1 plus 2 over 3 to the n. Now what happens if you when you send it, the n goes to infinity? When n goes to infinity, there will be 1 over 1 plus 0, which is 1. And that's not 0. So, by divergence test, the series is divergent. Let's do more. Let's say, for example, number 40. The series of 3 over 5 to the n plus 2 over n. This is equal to the series 3 over 5 to the n plus the series 2 over n. Okay, now then notice that this part here is harmonic. But this series see, I rewrite that as harmonic series, 2 times harmonic series is harmonic series. So the series is divergent. Therefore, the whole set, the whole series, because part of that is divergent, then the whole thing must be divergent. Okay, suggested homework from here. Number 27. I think I asked you to do some parts of that. Number 29. Actually, number 27 to number 47. To the options. Number 67 seems to be interesting. Number 67, think about it. That seems to be an interesting problem. What else? Number 84, that's theoretical problem. Actually, I would like to show number 80, from number 80. From number 80 to number 84. It's more into conceptual question. Try to think about that. This 11.2 will not be in your test 3, so don't study this until you are done with your test 3. Okay. Let's go to 11.3. 11.3 integral test. I have a message I didn't see. Why can't we use L'Hopital rule earlier? It must be something a lot earlier. The one here? You see the one here? Because a series is not continuous. You can only use L'Hopital rule when you have continuous function. Okay? It has to be continuous. Okay, 11.3 on integral test and estimate of sum. The integral test and estimate of sum. It has something to do with the graphical interpretation. So let's start with let the series from n equals to 1 to infinity of a sub n be equals to a sub 1 plus a sub 2 all the way to a sub n all the way to a sub infinity. Now I will graph this first. Okay, so let's say n equals to 1 is here, n equals to 2, n equals to 3, n equals to 4, and on. Okay, and a sub 1, let me make it here. A sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and on. Now, the total sum of a sub 1, a sub 2, a sub 3, and on can be seen as the sum of the following rectangle. So I extend it to the right. I extend it to the right. Okay, I extend it to the right. And let's say let fx be a function, a continuous function, such that fn equals to a sub n. So this continuous function will be like this. Now notice that the area under the curve fx from 1, integral from 1 to infinity of fx dx, is less than or equal to the series, the infinite series. Can you verify that pictorially? Pictorially, you see the area under the curve, the red one, actually this part. Now the sum of the series has the extra here. The sum of the series, or each term, has extra here. Right? Does it make sense? Okay, so the infinite series is actually greater than the integral from 1 to infinity. Is it okay? Now, I will do a similar picture. I wonder if I can copy paste this. Okay, I will do a similar picture. No. What am I doing? I will do the similar picture, copy, and okay. But this time, my graph will be done in the following way. I want to erase this. Okay, good. Instead, I will do it this way, going backward. Notice that this is A2. right? This is A2. So the infinite series starting from 2 is always less than the integral starting from 1. Why? Because the total area of these boxes is less than the area under the curve by this much. Okay? So the integral from 1 to infinity of fx dx is greater than, to be safe, equal to the series, but not from the first term. We start from the second term of the sum n. In short, conclusion. So from those two pictures, we see the following. From those pictures, we see the following, that the infinite series from 1 to infinity is bounded above by the integral. Can you follow me so far? That's from the first conclusion. The one here. Look, I think I write it the other way around. The other way around. This should be true. From the second conclusion. Right? So then, consequently, the infinite sum from the first term is less than equal to integral from 1 to infinity of fx dx plus the first term. Why does it have to be from n equals 2 again? From the way I graph it. From the way I graph it here, you see that the height here is actually from the second term, not from the first term. You see that? Okay, so here's the conclusion then. So we have that. Therefore, if the integral is convergent, then the series is convergent. It's bounded above, right? I need to first say that the series, the terms are non-negative. Or the terms non-negative, cannot be negative. So you see the series is an increasing terms, right? Because you keep on adding something positive and bounded above. Right? If a sequence is increasing and bounded above, then by monotonic bounded theorem, that sequence is convergent. If you see the series as a sequence. Now, on the other hand, integral from 1 to infinity of fx dx is less than equals to the infinite sum from 1 to infinity. So if the integral from 1 to infinity fx dx is divergent, then the series also divergent. So here's the integral test. Let fx be continuous positive decreasing function on, we just need it from 1 to infinity on the interval 1 to infinity. And fx is the superposition function where fn equals to the term. Oh, what happened? What did I do? Oh, what happened? Okay. Why it's moving? Positive decreasing. And fn equals to the nth term. Then the series, infinite series, and integral of that function from 1 to infinity are both convergent or both divergent. Now, it does not say that the integral equals to sum. No. This test does not say, does not claim that the sum, the series, equals to the integral. No, that's not what it is saying. Does not claim. It just claims that they must have the same convergence, the same convergency. Or divergence. Both of them convergent or both of them divergent. Okay, that's the first note. The second note, we just need eventually decreasing. So it doesn't have to be strictly decreasing from n equals to 1. As long as it is eventually decreasing, then it is fine. Okay, one classic example. Test if this series of, let's say, 1 over n squared plus 4 is convergent or divergent. So instead of well, it's definitely not a geometric series, right? In fact, you can imagine, you can say let the function fx equals to 1 over x squared plus 4, right? Note that this function is a superposition function. Okay? So fx is continuous on all real numbers, right? Happens to be. Therefore, it is continuous on one to infinity. I check the condition. Second, fx is greater than 0. Okay? Because x squared plus 4 is strictly positive, so the reciprocal must be strictly positive also. How about the fact that fx is decreasing? How do we show that fx is decreasing? We do the first derivative, right? Okay, so this will be negative 2x over x squared plus 4 being squared. And this is negative 4 x greater than 0. So f prime x is negative on the subinterval from 1 to infinity also. Now then, this fx satisfies the condition that it is continuous, non-negative, and decreasing on that interval 0 to 1. Now perform the integral test. Integral from 1 to infinity of 1 over x squared plus 4 dx. That's equals to limit t goes to infinity of integral 1 to t 1 over x squared plus 4 dx. Do you remember what's the integral for this? 1/2 tangent inverse of x over 2 from 1 to t. That is equal to 1/2 times limit t goes to infinity of tangent inverse t over 2 minus tangent inverse 1/2. What is this equal to? Pi over 2. So this is pi over 4 minus 1/2 tangent inverse 1/2. Right? That's convergent. Since integral from 1 to infinity of 1 over x squared plus 4 dx is convergent, the integral of superposition function is convergent, then by integral test, the series is convergent. Okay, now let's take a break. We come back at 9 o'clock. We continue with some more exercise. Let's continue. Can I start? Yeah. From here, we learn something called P series. Something called P series. P series infinite sum of 1 over n to the p is convergent when p is greater than 1, divergent when p is less than equals to 1. So if you happen to see a p series, you just need to see what's the exponent on the denominator. Okay, proof. You can say this is p series test. We just call it p series. A proof. Let fx be 1 over x to the p. Note that fx is continuous and positive and decreasing on 1 to infinity. Okay, and of course this fx is superposition function for for the sequence. Now, integral from 1 to infinity of 1 over x to the p dx is equal to, I need to break it up into some case. Okay, I need to break it up into some case. The first case when p equals to 1 first. When this is limit t goes to infinity of integral 1 to t of 1 over x dx. This is limit t goes to infinity 1. Oh, actually, I can do the ln, but that's natural log of x from 1 to t. This is limit t goes to infinity natural log of t minus natural log of 1. But natural log of 1 is 0. And this goes to infinity. So when p equals to 1, it is divergent. Okay, and it's actually pretty clear when p equals to 1. Note extra work. Note that when p equals to 1, we actually get harmonic series. Right? It's harmonic. So this series is divergent. Yeah, we just want to show that even we know that harmonic series is divergent, it turns out that the harmonic integral is also divergent. Okay, second, what happens if p is not equals to 1? Let's say p is greater than 1. So that's integral from 1 to infinity of 1 over x to the p dx. That's limit t goes to infinity of integral from 1 to t 1 over x to the p dx. That's limit t goes to infinity of 1 over 1 minus p of x to the p minus 1. See, right? From 1 to t. So this is limit p goes to infinity of, actually I want to bring that 1 over 1 minus p outside. Oh, that's 1 over 1 minus p outside. And then I get limit t goes to infinity of 1 over t to the p minus 1 minus 1. Okay, but p is greater than 1 means p minus 1 is positive. Is that right? P minus 1 is positive, such that we will get this is 1 over 1 minus p. The limit goes to 0 minus 1. So this is equals to 1 over p minus 1. Okay? Since integral from 1 to infinity over 1 over x to the p dx is convergent, then the series is also convergent for p greater than 1. Actually, for the same reasoning, what happens when p is less than 1? Then p minus 1 is negative, right? Then we will get 1 over 1 minus p limit t goes to infinity of t to the power of 1 minus p. See, if p minus 1 is negative, then 1 minus p is positive. Agree? but the t goes to infinity. Right? Then it goes to infinity. It's divergent. For p less than 1, integral from 1 to infinity of 1 over x to the p dx is divergent. Then the p series for p less than 1 is also divergent. Okay, now let's do this kind of problem first. Let's do this kind of problem first. Let's say, for example, I pick question number 4. The summation n from 1 to infinity of 1 over n to the 5th. Well, this is solution. This is P series. Once you identify that's P series, what is the P? The P is 5, which is greater than 1, right? Okay, so this series, therefore, is convergent. You can go back and argue that this is actually you can use integral test, but since it fits the P series, then we are actually done. Number 6. The series from 1 to infinity of 1 over square root of n plus 4. So you start from 5, huh? Right? You start from 5. This is the series 1 over square root of m, let's say, where m start from 5 to infinity. Is that right? I do substitution. But notice that this is the P series when P equals to 1/2. Okay, let me copy paste this. So you can argue that this is P series P equals to 1/2, which is less than 1. So this series, and I need you to be explicit though. Don't just say the series is convergent. You need to write down what series you are referring to, because there are 3 series you are talking about here. Even though they're equal to each other, they be explicit which one you're talking about. Okay, that is divergent. That's for number 12. Let's see more. Number 6. I think number 12 is quite interesting. We have 1 plus 1 over 2 radical 2 plus 1 over 3 radical 3 plus 1 over 4 radical 4 all the way to infinity. Is it convergent or divergent? Then rewrite that as 1 plus 1 over 2 radical 2 plus 1 over 3 radical 3 plus 1 over 4 radical 4. That's the same tool in summation notation n equals to 1 to infinity of 1 over n radical n. See, right? But this is equal to the infinite series of 1 over n to the power of 3 half. Now, make sure you give the argument, the reasoning. This is P series. What is the P? 3 half, which is greater than 1. So, according to the P series test, then this series is convergent. It's more about your argument, okay? How you rewrite that, make it look like a P series, and then see what's the P. Number 14. We have 1 over 5 plus 1 over 8 plus 1 over 11 and on. Then you argue this 1 over 5 plus 1 over 8 plus 1 over 11 and on in summation notation looks like what? You keep on adding 3 on the denominator, right? So that will be 3n plus 2. You see that? When n equals to 1, the denominator is 5. When n equals to 2, the denominator is 8. Now then, how do you argue that this is convergent or divergent? There are actually many ways to do this thing. Of course, one of them, if you want, you argue using integral test. So you say let fx equals to 1 over 3x plus 2. Okay. Note that this fx is continuous on all real numbers except negative 2/3. So consequently, it is continuous on 1 to infinity. Second, fx is positive. Why? Because, actually I should say fx is positive on 1 to infinity, because 3x plus 2 is greater than 0 on 1 to infinity. So the reciprocal is also positive. Now, how do you show that it is decreasing? Actually, because 3x plus 2 is increasing. Is that right? Therefore, the reciprocal must be decreasing. Okay? Now then you do the integral. Integral from 1 to infinity of 1 over 3x plus 2 dx. This is equal to limit t goes to infinity of 1, integral from 1 to t, 1 over 3x plus 2 dx. This is equals to limit t goes to infinity of 1/3 natural log of 3x plus 2 from 1 to t. Okay, so this is 1/3 parenthesis limit e goes to infinity of natural log of 3t plus 2 minus natural log of 5. But this will go to infinity. So by integral test, the series is divergent. By the way, that's only one way to do it though. That's one way. Number 14, right? Let me show you another way to do it. This series here, I summarize it right away. That's 3n plus 2, right? Notice that it is linear on the denominator. Okay. I want to do comparison test. I want to bound it below. Notice that it is, maybe I do it this way. This is the same to, let me factor the 1/3. 1/3 times 1 over n plus 2/3. Is it right? But this must be greater than 1 over n plus 1. Now this one, you think about it a little bit. I divide by something larger. I divide, this guy is smaller than this, right? But because I divide by something larger, then the quotient will be smaller. Now that guy is equals to 1/3 the summation from 2 to infinity of 1 over n. Change the n to m maybe. Do you see that? Okay, but this series here is harmonic. Okay, which is a lower bound of the series, the original series. So the original series, which is greater than the first, the last one, the harmonic, is divergent. You bound it below. Okay, that's for number 14. How about number 16? I look at the problem, honestly, I don't know what to do. But hopefully the following works. I want to say that let fx equals to x squared over x cubed plus 1. You need to show that fx is continuous on 1 to infinity. NTS stands for need to show. We need to show that We also need to show that fx is positive on 1 to infinity, which is quite easy to show. And then the third one is fx is decreasing, at least eventually decreasing on the interval. Okay, you need to show that. I do it fast forward. Then my plan is I want to do integral tests. Okay, which is equals to limit t goes to infinity integral 1 to t of x squared over x cubed plus 1x. Use U substitution. So now I have limit t goes to infinity integral when x equals to 1, this is 2. When x equals to t, that's t cubed plus 1. That will be du over 3, and this is 1 over d. So I get 1/3 natural limit t goes to infinity of natural log of absolute u from 2 to t cubed plus 1. This is infinity. So by integral test, that series is divergent. I think in the next section you will see we can do it a lot. We can actually do it a lot faster. For that one. We can do that one a lot faster. In the last 20 minutes, I want to show you something I usually don't ask. I usually don't teach also. But it's useful, especially if you are in computer science. Reminder estimate. Reminder estimate. It says that let the series be convergent. Let's say it's convergent to S. Okay, and the nth partial sum is the sum of maybe I use I here. The sum of the first n terms. So you see the following. You see the following. The summation infinite sum which is n, is actually the sum from 1 to n of that a sub I plus the summation from n plus 1 to infinity. Let's see it this way: a sub 1 plus a sub 2, a sub 3, up to a sub n, and then a sub n plus 1 all the way to infinity. Now this is the s sub n. Okay, and we will call this Rn. Where the Rn is the remainder of the nth partial sum. Now, this Rn here will be bounded above by integral from n to infinity of fx dx, and bounded below by the integral from n plus 1 of fx dx. Where the function fx is continuous, positive, decreasing on interval n to infinity. So even though I said earlier that the integral and the series are not equal, the integral and the series are not equal, it does not claim that. Okay? Even though they are not equal, but they actually approximate pretty well. Okay, they actually approximate pretty well. Now, how close they are, it will be as given by this integral. Okay, now let's see question, for example, question number, which one? Number 36 first. I try to do two problems. I do number 36 first. Number 36, we have this series. The series of the p series when p equals to 4. Okay, now part A, find S10. Basically, you need to do 1 over 1 to the 4 plus 1 over 2 to the 4 plus 1 over 3 to the 4 all the way to 1 over 10 to the 4. Okay? Do you want to use calculator for that? That's the same. If you want to punch it fast, this is 1 plus 2 to the negative 4 plus 3 to the negative 4 all the way to 10 to the negative 4. I will spend some time to do that. Or should I, you know what? I will just use Excel. I wonder if I have Excel here. So, yeah, I do. Here's my Excel. So This is 1, 2, and on. If you know Excel, that would be so good. And this is equal to whatever that is to the power of -4. So I add them. This is what I get. So this is 1.08203658. The question is, how accurate is this? How accurate is this? So what is the remainder? So R10 will be less than integral from 10 to infinity of 1 over x to the 4th dx. So the error will be less than that. Okay, this is limit t goes to infinity of 10 to integral 10 to t x to the -4 dx. So that's -1 over 3 x to the -3 from 10 t. You'll see this is 1/3 times 1 over 1000. Fast forward. Okay, fast forward. So the error will be less than 1 over 3000. Oh, but at the same time, this R10 will be greater equals to integral from 11 to infinity. You see? When you add the first 10 terms, then the error will be less than that, but more than this. Okay? Fast forward. This is 1/3 times 1 over 11 to the 4th. Okay, so this remainder is actually more than 1/3 times 11 to the 4th, but no more than 1 over 3 times 10 to the 4th. So think about this. Think about this. On the number line, S10 is 1.08203658. Okay. Now you suppose the infinite sum, should be this guy, is this and that. So this guy here is S10 plus 1 over 3 times 11 to the 4th. And this guy here is S10 plus 1 over 3 times 10 to the 4th. to improve the estimate. So we estimate S10 to be equals to S, right? Okay, now I want to improve this. To improve this S10, I will do the following. I will say that S now being approximated by S10 plus the average of those two. 1 over 3 10 to the 4th plus 1 over 3. I'm sorry, 11 to the 4th, 10 to the 4th over 2. Yeah, because we need to, I know I need to add at least by this, at most by that. I assume this S in the middle of those two, right? So I just get the average of that. So that's S10 plus 1, 6 times 1 over 11 to the 4th plus 1 over 10. Okay, let me use my calculator. Let's go back to Excel. Let me go back to Excel. The 11th term will be here, right? You know what? Let's improve the. Okay. Now then, this is the n. This is the a sub n. Is it okay? I wonder if you are with me. Okay. I will add these two guys, this guy plus this guy divided by 6. That's the number. I wonder if I can. It's e to the negative 5. You see what it means? Do you know what it means? No, I don't want to do scientific. I'll change it to number. More decimal point. Likewise here. Change it to number. More decimal places. Okay. So our estimate earlier, I will need to add, to improve the result, I will add this number. Sorry. I will add this number. What was that? 1.08. Too far. 1.08203. 1.08203. 6583. 6583. I'm sorry, I like this very much. So my improved estimate will be 1.08203 6583 plus 0.12340 280502. I get 1.082064633. Okay, so I estimate my infinite sum by this. Not only that I know the error, not only I know that the error will be less than 1 over 3000, but it is more than 1/3 of 1 over 11 to the 4th, right? Now then, by imagining that, I take the midpoint. Now I have a new estimate. I want to show that this number here is actually quite accurate. Okay, how to do that? Let's go back to our Excel. Let's go back to our Excel. And I will do the sum of n here, in which the sum here is the number above plus the term there. Okay, now let's bring this to infinity. Improve that further. Let's go up to 65 terms. 64 terms. So S64 is, oops, why am I, as I go to the 64th term, this is what I get. Am I adding them incorrectly? Let me see. Something not right here. Oh yeah, that's right. Change this to number, and then I want it to be this one here also. See how much off it is. I somehow think, am I actually computing this incorrectly here? I'm sorry, I'm now at my notes, not my Excel. So my R of 10 will be 1 over, I'm sorry, 1 over 3,000. Oh, not 3,000, that's 30,000. Am I computing anything wrong here? The difference here is too big though. The difference here is too big. 1.0823219992 subtract by 0.1. This is big difference. Am I computing something wrong? This is 0.0003. Oh yeah, it's actually 2.6 something approximately. So it is less than, this guy is less than 1 over 30,000. Is it right? Unless I computed incorrectly. No, 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 no. Sorry, my bad. I actually copied numbers wrong. My bad. I copied numbers wrong. This is 11 to the third. So this is to the third. This is to the third. This is to the third. This is have too many zeros. That's why then I make mistake here too. So this number is incorrect. This number is incorrect. Oops, how do I cancel that? This number is wrong. How do I delete that? Okay, miscomputation. I need to go back there earlier. This one is correct. So this is a miscomputation here. This is miscomputation here. Erase that. Yeah, good thing I checked. So I need to delete this. My bad. The time's already up, but I need to fix this though. I need to fix this. Let me just use my calculator. 1/6 times 10 to the 11. 11 cubed to the reciprocal plus the reciprocal of 10 to the -3 divided by 6. I get this is 0.00029188. So what will that be? Plus 1.082036583. This is 1.08232849. That's what I get. Okay, now let's see the difference between what I estimate compared to the sum up to 64 terms. The sum up to 64 terms. This is 21992. Seven, 4, 6. So it is accurate to 5 decimal places. Not bad. I really wish I can do more. But your suggested homework from here, I would like you to do number 3 to number 25, number 29, 31, 34, 35, 37, 38. I guess that's it. Okay, so remember that you have a test on Wednesday. That will be up to 11.1. Then after the Wednesday, study this suggested homework. Then on Monday, I will do 11.4, 11.5. Okay, so next week we do up to 11.5. See you then.
Thank you.
Thank you. Good job, by the way.